In this video, we'll learn about cyclohexanes. Previously, we looked at cyclopropane, butane, and pentane. So we looked at our smaller cyclic rings. Now we're going to focus exclusively on cyclohexane because cyclohexane occurs widely in nature. It's one of the most common ring shapes you see in nature. And the way cyclohexane exists is it adopts what we call a chair conformation. The chair conformation is a strain-free three-dimensional shape. So in the chair conformation, the ring no longer has any angle strain or torsional strain. And so if we look at our cyclohexane and what we mean by chair conformation, is this is what it looked like in a model. And if we were to draw the line structure, it would look like this, where all the hydrogens are either pointing up or kind of to an angle. And so if we were to look at the ring across these two bonds, so we're looking at it across bonds 4 and 5 and 1 and 2. And we draw its Newman projection, it would look something like this, where the two CH2s are in the middle. That would be number 6 and number 3. And then on the two that we're drawing as Newman projections, you can see the hydrogens exist in a nice staggered conformation, where we have them either pointing straight up or straight down, or at an angle in opposite directions. One's angling up, the other's angling down. This is how we've reduced all the angle strain, because now we're able to get angles of 109, and we've also reduced the torsional strain because there really isn't any overlap between these. So this is how the chair conformation and the 6-membered ring are one of the more widely seen rings in nature. So looking at our conformation, we just saw the chair. So our chair conformation would look something like that, where we have one corner points up, the other corner points down. Another conformation we occasionally see in nature is what we call a boat conformation. And you can see it kind of looks like a little boat. This one kind of looks like a little lounge chair, pretending like your head's here and you're sitting on it. Here's your boat. And in the boat, many of the hydrogens are eclipsed. And there's a little bit of steric strain with the two flagpole ones. So that'd be a hydrogen here and here. So you can draw little flags on them. But we do occasionally see boat conformations. And looking a little more at these chairs and boats. And so if we're to draw the chair conformation in our Newman projection again, it would look something like this. Where you can see we've minimized our strain, our axial, we've minimized all of our strain. Our boat conformation, if we draw that as a Newman projection, could look something kind of like this. And so what happens is with the chair conformation, the axial bonds or the ones we call the axial hydrogens, those are pointing directly up or down. So that would be an axial hydrogen. That would be another axial hydrogen. And then the other two are what we call equatorial hydrogens. And that's because they're kind of near the equator part of it. And so those equatorial ones, they point outwards away from the ring. In the boat, we can see we have a lot of axial hydrogens that are overlapping. Instead of being just a regular boat like this, what it's going to do is it actually exists as a twisted boat, which becomes nearly free of our angle strain. So what a twisted boat looks like might be something more like that. Or you can think of it as a boat. It's probably going to start sinking. It's not going to hold off the water very well. But you can see how with the boat, it kind of twists a little bit, and that will reduce our angle strain. So now we're back at the 109 degrees. Now I'm sure you're asking yourselves, how do I actually draw a chair conformation? Trying to draw it yourself? Not that easy. Chair conformation usually takes a little bit of practice before you get good at drawing it. So what you're going to do for drawing your chair conformation is you want to draw two parallel lines slanting kind of downward and slightly offset from each other. So that looks like something kind of like that. Slanting kind of downward and slightly offset. Then we're going to place our topmost carbon atom above and to the right of the plane of the other four. So it might be something up here. Then connect the bonds. Boop, boop. Not too bad so far, right? You with me? Now we're going to place the bottommost carbon atom below and to the left of the plane. So kind of repeat the process. Put it down there. So we're going to repeat the process on the other side. And then connect the lines. Boop, boop. So also, if you notice, this bond and this bond are parallel to each other. This bond and this bond are parallel to each other. So if you're able to draw a ring like this, good job. Please do not do rings like that. Also, do not do rings like that. Yes, I have seen both of those rings drawn, and they're not good rings. The reason they're not good rings is on this one, your hydrogens would look like that. Or if you're trying to be kind of sneaky, you might draw it like that. So you can't tell which one is axial, which one's equatorial. Which means if you draw a ring like this and you're supposed to determine axial and equatorial, you can't tell it here. And if you can't tell it, I can't tell it. If I can't tell it, it's not correct. It gets marked wrong. So I'd recommend practice drawing rings, get a little bit better drawing your chair conformations. Once you're good at chair conformations, then you can easily tell axial and equatorial when you draw the hydrogens. So now that you've practiced and gotten good at your chair conformations, let's try and draw a chair flip. So 6-membered rings have different conformations within the ring because it can do a chair flip. What that means is it's going to rapidly change between these two conformations. You can see the difference is this hydrogen, instead of being pointed up, now it's pointed down. This one, instead of being pointed down, gets pointed up. So that's called a chair flip, which means you'll need to get good at drawing your rings. Not the best ring. There we go. In this conformation. Also in this conformation. So you should be able to draw your rings in both conformations. So practice drawing your chairs. It'll save you trouble later. Practice drawing both kinds of chairs. That way you can draw a ring flip and draw the chair flips. So now that you've practiced drawing your chairs, you want to start adding in hydrogens onto your chairs or adding in your substituents. So as you can see, our bonds pointing straight up and straight down. Those are our axial ones. And then the bonds that come off at an angle, those are our equatorial ones. So you can see when you're drawing your bonds and you're drawing the angles here, it's important to kind of keep the angle. Notice how the bond between the two carbons here is coming up. So the bond for the hydrogen is pointing down. So you can see the bond for the substituent coming off equatorial. It's kind of at the same angle as the ring. So that means if we were to draw the substituents or the angles on our ring, or on my ring I drew, it would look something like this. So you can see the ones where the point is pointing up, that axial is pointing up. The ones where it's pointing down, that axial is pointing down. And then our equatorial, so you can see if the axial points up, the equatorial has to kind of point downward a little bit. If the axial points down, the equatorial points up. And then these two in the middle, those tend to be the kind of weird ones to draw. So here, these two are pointing up and down. We're going to make this kind of come out at an angle that's similar to this. So that kind of signifies it's pointing downward. We're going to do the same thing with this carbon. Its equatorial bond is going to kind of point up and back. And the corners are usually the easier ones. And so you can see when I do a chair flip, anything that's axial here becomes equatorial here. Anything equatorial here becomes axial. But an important thing to note when you're doing your chair flip, you can think of it as whatever's on the bottom side of the ring stays on the bottom side of the ring. So if we were to have a methyl group here, you can see it's on the bottom side relative to the axial group, relative to the hydrogen. We'll draw hydrogen. And then this point here, this corner becomes this corner. So you can see the tips, you just take the tip and push it down. So now the one that was equatorial becomes axial, but it's still on the bottom. So that CH3 is still on the bottom compared to the hydrogen. So chair flip will change axial equatorial position, but it will not change whether the substituent is on the top side of the ring or the bottom side of the ring. That's an important thing to keep note of. Chair flips change axial to equatorial, but they do not change which side of the ring the substituent is on. So when you're doing your chair flip, don't make the mistake that I see a lot of times, where you'll do chair flip, you'll draw it correct, and then you'll take the top corner here and call it this top corner. That's not the same carbon. That one, if we count 1, 2, 3, 4, 5, 6, becomes 1, 2, 3, 4, 5, 6. So you can see if you called this one carbon 1 and you tried to call this carbon 1, that's not the same one. That's carbon 6 now. That's the one over here. That's in the middle still. It's not one of our points. So keep that in mind whenever you do a chair flip. All you're doing is changing the axial equatorial position. You're not changing whether it's on the top side of the ring or the bottom side of the ring. With all that said and all the practicing with chairs, let's look at something that's only seen in six-membered rings, and it's called a 1,3 diaxial interaction. So as we know, our substituents can either be axial or equatorial. So if we try and draw methyl cyclohexane and draw it as a chair. You may have drawn something kind of like this. Or let's say we do a chair flip with it. Or you might have drawn something where it's equatorial. Draw hydrogen there. Fixing it to make it look more equatorial. Because equatorial is at a little angle, it's not straight across. So make sure when you draw your equatorial, you don't draw it straight like I did by accident there. Make sure you draw it at an angle. So you could have drawn it either axial or equatorial. Didn't really matter which one, because all you do is a chair flip and you get the other one. But with our substituents, not all are created equal. Not all chairs are going to be the same. So what do I mean by that? If we have our methyl group equatorial, if we have our methyl group axial, I were to draw the hydrogens for the other corners. So if I draw the hydrogens for the other corners, these are all kind of in close proximity to each other. Same thing if we draw the other chair. These are all kind of in close proximity to each other. So there's some interaction between these, or between the methyl and the hydrogen. And the reason we call it a 1,3 diaxial, they're all axial as you see. And if we number our carbons, it's 1, 2, 3. So it's 3 carbons away. It's a substituent that's 3 carbons away that's also axial. They have interactions with each other. When they have interactions with each other, you create some steric interaction. And depending on the size of the group, you can have a really large steric interaction or a really small steric interaction. So as we know, hydrogens are smaller than methyl groups. So we can predict, since this methyl is axial, it's going to have some 1,3 diaxial interactions and some steric strain because of that with the 2 hydrogens. The hydrogen here, probably not going to have any because they're all really small. And so if we were to draw our ring again, whatever our group is here, we'll call it X, it's going to interact with the electron cloud on each of those hydrogens. And it's going to create that steric strain between the electron clouds there. So if we look a little bit at this 1,3 diaxial interaction, it's really just that Gauss interaction. If we remember from our Newman projections, a methyl group and a hydrogen had a Gauss interaction, had some energy. So if we look at the Newman projection of our ring, we can see if we have a methyl group here, and our hydrogens back there, it's really just the Gaussian interaction occurring here. So because they're in close proximity, you get your Gaussian interaction. So this would be if we had it axial. And then if we had it equatorial, see when it's equatorial, that CH3 group is pointed away from the ring, is pointed away from everything. So there wouldn't be any interactions. It's really just that actually you start getting that Gaussian interaction. And so the larger this group is here, the larger the substituent, the larger the energy difference. Which means when we're looking at our chairs, for this example here, about 5% of it is going to be where you have that axial CH3. That 95% is where it's equatorial. Big difference with just a CH3. And that has to do, there are numbers here again. And that has to do with that Gaussian interaction versus no Gaussian interaction. Nature and compounds always want to be in the most stable configuration. So if we're looking at all these different strains, each substituent has its own number. And so you can see some of them are really small. Fluorine, not really big of a difference, just a little bit. Versus if we have a tert-butyl, that's a huge difference. Tert-butyl will almost always point outwards. Very rarely will you ever see a tert-butyl in the axial position. And if you make a model and you put a tert-butyl on it, you can see that tert-butyl will start hitting those CH3s. You can see that tert-butyl will start hitting those different hydrogens. And so you all should have a copy of this table. And so you can use the table to figure out the energy strain in the 1,3-diaxial strain for our different substituents. So far, we've been looking at everything with one substituent. What if we have two? With two substituents, we have to think more about how we draw our compounds. Also, we haven't really looked at what a wedge and a dash mean when we draw our rings. So wedge and dash indicate whether it's on the top side or the bottom side. It does not, and I repeat, does not indicate axial or equatorial, just top or bottom. So let's look at an example of this. Let's say I give you the disubstituted ring, 1-chloral, 2-methyl cyclohexane. Just switch. So now here, I've given you some stereochemistry. These two groups are trans to each other. One's pointed up, one's pointed down. One's on the top side of the ring, one's on the bottom side of the ring. So one's on the top side, one's on the bottom side. When we draw our chair conformation of this ring, we have to keep that in mind. Chair. First, you want to draw your chair. After you draw your chair, you want to start figuring out the position. So we can call this 1, 2, 3, 4, 5, 6. So I can say 1, 2, 3, 4, 5, 6. So numbering all of my carbons here, I can see the chlorine is pointed up. The chlorine has to be on the top side of the ring. Looking at my two bonds coming off of carbon 1. This one would be the top side of the ring. This one would be the bottom. This one's higher up. This one's lower down. So that means my chlorine comes up here and my hydrogen points down. We do the same thing with the second one. The corner points down. The equatorial one points slightly up. Since it's a dash, that's on the bottom side. That means it's going to be my axial. So even though it's wedge and dash, they both end up axial. And if we draw a chair flip, we can see carbon 1's pointing up. Now carbon 1's going to point down. That means carbon 1, I'm going to have my two substituents. Here, the hydrogen's on the bottom side. Hydrogen stays on the bottom side. The chlorine, since the wedge, stays on the top side. And then my next one, carbon 2, hydrogen's on the top side, just like here. Methyl group is on the bottom. So methyl group is now on the bottom compared to the hydrogen. So here they both end up equatorial. Two end up axial, two end up equatorial. Still considered trans. And so if we wanted to predict which one is more stable, we can start to do that. Because think about your 1,3 diaxial interactions. With our first compound here, compound 1 versus compound 2. Compound 1 has two groups that are axial, which means my chlorine is going to have 1,3 diaxial interactions on the top and my methyl group is going to start having 1,3 diaxial interactions on the bottom. So this has a lot of interactions happening. With the other conformation, you can see the only axial ones on the top are hydrogen. The only axial ones on the bottom are also hydrogen, so there's no diaxial interaction here, which means this one is going to be a higher energy conformation. Which means number 2 is going to be the favored conformation. And so now you guys should be able to draw your chairs. And so now we've learned a lot about cyclohexanes. You should be able to draw your chair conformation, do your chair flip, draw your axial and equatorial substituents correctly, start to predict 1,3 diaxial interactions, and be able to predict which of those chair flips, which of those conformations is more favorable.